Welcome to section 4.2.2 on theoretical and experimental probability. The big question is, what is the connection between theoretical and experimental probability? I want to give you an example before we get too much further. If I were to ask you to flip a coin, heads and tails, you would tell me that if I asked you about half the time it's going to be heads and half the time it's going to be tails. Okay? We can tell that because the option for heads is 1 out of 2, or 50%. That would be theoretical. If I actually took the coin and I flipped it many times and I saw how many times it got on each, that is going to be experimental probability. And so we want to look at the connection. Some connected ideas to that today are also going to be using tree diagrams and tables. So we started with this question. They gave us this spinner and they asked us to first talk about it theoretically. So first, what results can I have? I can have A or I can have B. What do you think the chances of getting A or B are from this diagram? Well, I can kind of see that it looks like A is 3 times as big as B. So I would say that I have a 3/4 probability for A and a 1/4 probability for B, or 75% of the time I'll get A and 25% of the time I'll get B. That's the theoretical. Then they asked us to go in and they wanted us to make a spinner, but we're going to do it this way. We're going to go to our apps. And we're going to go to one of the applications as soon as it lets me, called Probability Sim. We had to go in. We had to change all sorts of things in here. We're going to spin the spinner. And we're going to make a few changes because our spinner didn't look right. Our spinner needs to have 2 sections. And we're going to go to the advanced. And we're going to change the probability of 1 to 75, and going down it changes the other. And now I'm going to get a spinner that looks pretty much like this one, except the quarter region is down here in the corner. We then cause this to spin, and we went in and we maybe can tell it to spin 50 times. And so now it's going to do that for us. And we saw that as we did this, it's modifying this and will let us know. I can use my arrow over. It tells me there's 40 of those and 11 of those. So out of 50, this is about 1/5, and that's about 4/5, or 80% and 20%. Pretty close to that. We don't have time on the video to do it more, but if you do it more and more, if you have that chance, right now, go ahead and pause and do that, then you'll see a pattern. Okay, the pattern that you saw is if you did it many times, say 340, then 400, that as we do that more and more, it begins to approach these values. So the theoretical, and the reason we use the theoretical is because it predicts the experimental very well usually. If we didn't, we would want to check and see if we needed to use a different model for our theoretical probability. Okay, the next question gave us 2 options, and this is what they kind of said. They said we're going to basically have this 2 spinners this time. The first spinner here, and then the second spinner here. So you can spin the first one to find the money, and then you either keep what you won or you get double. And they asked us to organize it and make it. And so if I make that, I'm going to do it into a table. And my table is going to have the original values, 100, 300, and 1500. And if I have the original winnings, I'm going to put that here, and this is the double winnings. So I could have 100 on the original, 300, or 150. And if I doubled it, I'd have 200, 600, and 3,000, I believe, is the right number. So inside the table is my values, and so I know it's out of 6. They asked us some questions. We can also do it as a tree diagram. Okay, so we saw that 100 double or keep, 300 double or keep, and 1500 double or keep. They asked us some questions. I'm not going to ask those, but about the different probabilities that we could get with that. Then they asked us a question about dice, and I spent a little bit of time on dice, and we made this chart. The reason to make this chart is because if I were trying to figure out all the possibilities for this, okay, 2 dice being rolled. Well, let's see. I could have a 1 on this one and a 1 on that one. A 1 on this one and a 2. A 1 and a 3. 1 and a 4. 1 and a 5. But you can see that as I do this, I'm going to get just a really long list. Okay? So I'm going to put it on this chart. This chart is not a multiplication chart. So I thought I'd better tell you because that's what both classes seem to think it was initially. Okay. So if I look here, this is going to be, for example, if I roll a 1 on one dice and a 1 on another. Well, I add those together and the value would be 2. Okay? If I roll a 2 and a 1, I get a 3. If I roll a 2 and a 1, I get a 3. Okay, just using some color. 3 and 1, 4, 4. And the next one, 5, 5, 5. Okay, this is 6. 2 and 4 is 6. 3 and 3 is 6. 6, 6. Okay. 7, 7, 7, 7, 7, 7. I promise you that I'm adding these right. I'm just doing this fast so that we can make it through before we run out of time. 7, 8, 8, 8, 8, 8. And 9, 9, 9, 9. 10, 10, 10. And 11, 11. And 12. Okay, the way I did the chart makes it kind of easy to see. You've got a diagonal 3s, 4s, and 5s. The longest diagonal is a 7, so the most chance you have is to get a 7. Okay, I connected it to some games. And so this allowed us to see it. What, for example, would be the chances of getting a 7? Chances of getting a 7 would be 1, 2, 3, 4, 5, 6. And there are 6 by 6 in this chart. So 6 out of 36. Now, they asked us if the events in this chart were independent or dependent. By that we mean, does the second or the next things we do matter on the first? Well, if I roll a 1 on the first dice, does it affect what I roll on the second? It doesn't. So that would be independent. So each of the dice are independent. If I took a card from a deck and then took another card from the deck, those would be dependent if I didn't put the card back in, because the probability on the first one would be 1 out of 52 and the second one would be 1 out of 51. Now, with this, they asked us some questions, and we answered them. But basically, if you made the chart, we could say, what's the chances of getting a number 6 or less? Well, we'd count those up and put them over 36, and that would give us our probability. What would the chances of getting an even number be? Well, I've got 2s and 4s and 6s and 8s and 10s, and so I could find those results or any particular number. I hope that this has helped. We didn't have a whole lot of time to do this, and your book goes into a few more questions in more depth, but I did want to kind of get that idea of independent and dependent over and across to you. Let me check one more thing. We did do on the graphing calculator, it will also do dice roll. The only thing that you'll have to do is go into your settings and change it so that it knows that you want to do 2. And then you could actually tell it to roll, and you could roll it many times.